Now we are on live on YouTube. Jörg, whenever you want, you can.
I was about to ask, shall we start on time? And what I say is not that important anyway. So, okay. Welcome everybody to this second week of the online Invisibles School. This week, it's a very great pleasure to have Jane Kamenik, who kindly agreed to talk about Flavour and effective field series, which I think is a particularly timely topic in light of, as we just kind of chatted about a little bit, of the new results of G-2. Welcome to Jane, but also to everybody participating in this school. So I would say, without further ado, Jane, please.
Okay, thank you very much for the invitation and for giving me this this task, which is, as you said, it's very timely, and I'm sure there's a lot of interest in flavor physics recently. And so I hope to do justice to the topic with the limited time that I have available. So I will just let me share a little bit to start. Okay. Do you see the slide?
Yes, we do.
Okay. So let me start by giving you a couple of main references upon which these lectures are based upon. I hope that by the end of these lectures, I'll be able to also, through the organizers, to share these slides with you, so you can have them for later references. Technically, I plan to combine whiteboard lectures, because I think the pace is then more manageable for you to absorb, and with these combining with some slides where I have some plots and results, which are easier to represent in terms of slides. So to start, the plan of these lectures is roughly the following. I hope to come to the end with this. So today, I'll mostly discuss the first two topics, basically defining what we mean by flavor, and then discuss what are the flavor parameters and flavor dynamics in the Stata model. Tomorrow's lectures will be more technical, in the sense that I will go into the details of the Ckm parameterization of the flavor in the Stata model, of the flavor processes and the flavor parameters of the Stata model, and how we measure them. And in particular, because CP violation in the Stata models is, in particular in the Stata model, CP violation is tightly connected to flavor, which is very particular. And so I will also discuss in detail how we measure the CP violating parameter, the one CP violating parameter in the Stata model, in the flavor part of the Stata model, and how this is connected to the phenomena of neutral meson mixing. And then the last lecture on Thursday will be devoted first to the concept and the technology of the use of effective field theories, with some examples, both in the starter model and also beyond, and how we can use these techniques to efficiently probe standard model and potential new physics using low energy flavor observables, like the G-2 of the muon, for example, if we think of it as a flavor observables, because as we'll see, it actually does break some of the flavor symmetries of the standard model. Is related to the breaking flavor symmetries. Okay, so so first I will discuss what we mean when we talk about the flavor, and I will just switch now to a whiteboard. So let me see if I manage to do it. Okay. So I need to promote my other account to be allowed to share. So let me see if I'm able to do it. I have to find myself. I see I'm not, so maybe Luca can help me. I don't seem to be able to promote my other account to co-host so I can share.
Okay, which is your other account?
It's the same name. It's just with this account I'm co-host, but then there's another account on my name, which I would like to be allowed to share content because this is my tablet.
Let me check where it is. It starts with the Faisal as well.
Yes, yeah. It's the same. In my participant window, it's at the very bottom.
Very bottom. Yeah, now I can see it. Make host. You should be able to do that now.
Okay. So let's see. Okay. I need to stop sharing here. Let's see. Stop share. And now I can. Okay, perfect.
Perfect. Now we can see the tablet.
Okay, perfect. Thanks. Yes, so let's discuss what we talk about when we talk about flavor. Now, and let's frame this discussion in the context of the standard model where it's originally introduced. So in the standard model, the basic constituents of matter are excitations of fermionic fields. So spin 1/2 fields. And we define matter flavors in this context as several copies of the same gauge representation of these fermionic fields. So in particular, under the unbroken standard model gauge group, which is of course SU3 of color times U1 of electromagnetism, we have the following gauge representation of fermionic fields. We have so-called up-type quarks, which are triplets under color with a charge, electromagnetic charge 2/3. And the flavors of these up-type quarks are conventionally denoted by U, C, and T for up, charm, and top. Then we have down-type quarks, which are again form triplets under color, but with electromagnetic charge -1/3. And the flavors of down-type quarks are D as B for down, strange, and bottom. Finally, we have the uncolored fermions, namely the charged leptons, which are singlets under color, but with an electromagnetic charge, electric charge -1. They again come in 3 copies, namely the electron, the muon, and the tau. And finally, we have the neutrinos, which are singlets under color without an electric charge. And let me denote them by nu1, nu2, and nu3 if we talk about the mass eigenstates. So the main point of Flavour is that these different copies of the same gauge representations differ only in their mass. So the different copies differ only in mass. Now, how does Flavour relate to the matter that is around us, and where do we actually observe, or historically where these different copies have been observed? So in particular, ordinary matter is essentially the so-called first generation, so the first copy. So up, down, quarks, electrons, and neutrinos. So ordinary matter is essentially first generation. So up and down quarks are bound within nucleons, so protons and neutrons. Electrons, so these nucleons or nuclei bound with electrons to form atoms. And what we historically call electron neutrinos even though they do not correspond to this notion does not correspond to a mass eigenstate of neutrinos, but is in fact an admixture of nu1 to 3. So these electron neutrinos are produced in fusion reactions inside stars. On the other hand, all the fermions, all the matter particles of the second and the third generation families are produced only in high energy collisions. And they are being unstable, they decay via weak interactions back into third generation particles. So now that we've roughly defined flavor, we can also come to some of the biggest questions which are still open in fundamental physics. And these are why there exist three almost identical replicas of quarks and leptons. So there seems to be no structural requirement within the standard model to have these three copies of our matter fields. So why three almost identical replicas of quarks and leptons? And secondly, what is the origin of their different masses? So why are their masses so different? In fact, their masses span several orders of magnitude, even within a particular gauge representation. So while the standard model is able to parameterize these different parameters, which at the end can accommodate the different masses of the standard model of the fermionic field, of the fermionic particle of matter particles, except the neutrinos in its original formulation, it does not actually explain the hierarchies that we observe. It parameterizes them, but does not explain them. And this is most glaring, of course, in the case of neutrinos, where the originally formulated standard model does not even account for neutrino masses. And actually, I should just state here that the origin of neutrino masses actually deserves a completely separate set of lectures. So in the course of the three that I'll be giving here, I'll mainly focus on quark flavor relation, with a little bit of a discussion on Thursday, referring also to lepton flavor relation related to the recent recently reported interesting measurements, both with respect to the G-2 muon, and especially on rare seminatomic B decays, where there seem to be indications of lepton flavor non-universality, which I will discuss and I'll explain what this actually means. So in relation to flavor, we have a couple of notions or concepts that you will also often come across. And in particular, let's define them properly. So let's start with what we mean when we talk about flavor physics. So flavor physics refers to all interactions that can distinguish between flavors. And in particular, within the standard model, these are the weak and Yukawa interactions. So Higgs interactions and weak interactions. Connected to these are so-called flavor parameters. Flavor parameters are parameters that, at least formally, carry flavor indices. And again, let's make this more concrete within the standard model. In the standard model, we have the following flavor parameters. We'll proceed with the formal counting of these parameters later when we develop the theoretical tools for counting of flavor parameters. But for now, let's just state the flavor parameters. In particular, we have 9 masses of charged fermions. We have 4 mixing parameters in the quark sector, namely 3 CP even angles and 1 CP odd phase. And in particular, these parameters actually, in terms of phenomenology, they parameterize the interaction between the charged weak bosons and quarks, where the indices ij now are referred to as denote the flavors of the up type and down type quarks. So these interactions can be parameterized within the standard model with 3 angles and 1 phase. Now, if one was to add, so in the standard model, as I already mentioned, one does not account for neutrino masses. But for example, there is not a unique way to account for neutrino masses. But for example, if we were to add Majorana mass terms for all the neutrinos, so adding 3 singlet fermions to the standard model, then this would add to this model, which is the standard model plus 3 singlet fermions, would in general add 3 light neutrino masses and 6 mixing parameters, namely 3 angles and 3 phases, parameterizing the charge current interaction, so the W boson interactions with neutrinos and charge leptons, which would then become physical parameters in the low energy theory. Now, connected to these concepts of flavor, we often talk about flavor universal interactions. And these are interactions with couplings which are proportional to the identity in flavor space. So again, let's again define these flavor universal interactions within the standard model. These are, of course, QCD and QED interactions. They are, since by definition, all generations or all flavors of a given type of fermionic field carry the same gauge charges, the corresponding gauge interaction will be flavor universal. Sometimes you will also hear the notion of these interactions being flavor blind. So in terms of, if we think about flavor space, these interactions will be proportional to the identity in flavor space. Just for reference, note that also if we, as we will discuss in a few minutes, if we write out the standard model Lagrangian in its so-called interaction basis, then also weak interactions are in this particular basis are flavor universal. Of course, in the standard model, after electroweak symmetry breaking, the weak interactions become non-universal once we go to the mass basis, because the mass basis does not correspond to the interaction basis in the standard model. And a narrower concept than flavor universal is so-called flavor diagonal. flavor diagonal interactions are interaction with couplings which are diagonal in the mass basis, but they are not necessarily universal. So again, within the Salmon model, these are the Yukawa interactions of the Higgs boson. Again, this is all in the mass basis. Conversely, we often are within the discussion of flavor physics, we are most concerned not with these flavor universal interactions and a little bit with flavor diagonal, but mostly with so-called flavor changing processes. So we talk about flavor changing processes are processes where the initial and final flavor numbers are different. This means by flavor numbers, we mean that the number of particles with a certain flavor minus the number of antiparticles of that same flavor. And in particular, we can distinguish between a couple of different flavor changing processes that are interesting and are somewhat different. And first is the so-called flavor changing charge currents. Flavor changing charge currents. And these so-called flavor changing charge currents are processes where both up and down type quark flavors or both charged and neutral lepton flavors are involved. And let me give you a couple of examples of such flavor changing charge current processes. For example, this is the ordinary muon decay. Okay, is an example of a leptonic flavor changing charge current process. Or the charge Ckm leptonic decay. Okay, we can think about this charge Ckm decay at the quark flavor level as a decay of an initial state which has an S flavor and an anti-U flavor, and then it decays to mu minus nu I bar. Okay, so it involves both up and down type quarks, but also both charge and neutral leptons in this case. Again, let's see what is the characteristic of flavor changing charge currents within the Salmon model. Here they are mediated with through a W exchange at true level. So W exchange at true level. So they appear at first order in perturbation theory of weak interactions. Consequently, at low energies, the amplitude for such processes, the amplitudes are proportional to the Fermi constant, G Fermi. We'll discuss the correspondence within the W exchange in the electroweak theory and the Fermi constant in more details in our Thursday lecture on effective field theories, where this is one of the examples. So in contrast, within the we also have so-called flavor changing neutral currents. And these involve either up or down type flavors, but not both. And conversely, on the lepton side, they involve either charged lepton flavors or neutrino flavors, but again, not both. And again, perhaps it's easiest to just state a few examples. On the lepton side, a flavor changing neutral current process would be a radiative muon decay to an electron and a photon. And the corresponding on the hadronic side, to have the correspondence with the charge current process above of a charged lepton, we can consider the K long, so the long-lived neutral kaon mass eigenstate decay to a pair of mu plus mu minus. Okay. Again, at the level of quark flavors, this is a transition from an S bar D flavor state to a mu plus mu minus flavor state. In fact, K long is technically is an admixture of S bar D and D bar S. But for simplicity, I've just stated one of these here. Again, let's see what characterizes flavor changing neutral currents within the Staller model. Within the Staller model, contrary to flavor changing charge currents, the neutral currents occur only at higher orders in the weak expansion. So typically, this involves loops, okay? And they are often highly suppressed compared to charge currents. So these are the main concepts. Lastly, let me briefly introduce a final concept which I will discuss in more detail, especially in the last lecture. And this is the concept of flavor violation. And I will define the concept of flavor violation a bit later when we've introduced flavor symmetries. And then it becomes clear what is actually being violated when we talk about flavor violation. So let's conclude this introduction with a couple of historical examples of why studying flavor physics or flavor processes is interesting and can lead into deep insights about fundamental physics. So,
Yeah. Sorry, there's a question. Could you give an example of diagram for this flavor change in neutral?
Oh, sure. So, for example, let me, for example, give it for the second one. So the K long to mu plus mu minus. So one possible example of a diagram would be, maybe let me, yeah, I can do it this way. So it would be, let's say I have S and a D bar, and I mediate through a box of W's, and there is an up-type quark in here, and then I have plus mu minus, and there is any kind of neutrino. So this is one example of a loop diagram which mediates. It's not the only, so there are several loop diagrams which mediate this process, but this is one example of one such diagram.
Okay, thanks a lot.
Okay. Yes, so let's discuss a couple of examples why flavor physics is interesting. So there are a couple of general answers to this. One is that using flavor physics, and this is actually true for other types of precision low energy measurements. And this is that one can discover new physics. By new physics, we mean yet unknown dynamics, or probe it before it is directly observed in high energy experiments. What I mean by that is that we can infer on the existence of some new degrees of freedom before we can actually produce these degrees of freedom on shell in high energy experiments. And let me give you an example, a historical example of this, is that the measurement of the ratio of these rates, which I've written above, so the measurement of the ratio of the rates of k long to mu plus mu minus over the decay width of, or decay rate of k plus to mu plus neutrino, which is very small but non-negligible, led to the prediction of the charm quark. Furthermore, actually, the measurement of a different process in Ckm physics, one which we will discuss a lot tomorrow, which is the oscillation frequency of neutral kaons, which is related to the mass difference. So the so-called delta mk, which is the mass difference between the long-lived and the short-lived neutral kaon state, actually led to the prediction of the charm quark mass. Much later, a similar process, namely the measurement of the oscillation frequency of neutral B mesons, which is defined technically as the difference between the heavier neutral B meson state and the lighter neutral B meson state, led similarly to the prediction of the top quark mass. And this was in the 80s, so more than 10 years before the top quark was actually discovered at the tevatron. And finally, perhaps the most astounding prediction historically was the observation of a particular kaon decay, namely the decay of k long to pi plus pi minus, or in modern terms, the measurement of the CP evaluating parameter in the kaon system called epsilon k. So you will notice, so what this decay signifies is that the CP parity of the initial and the final state are different. And so this decay, so the observation of this decay indicates that CP is not a good symmetry of nature and that CP is broken. And within the standard model, this actually led to the prediction of the existence of a third generation of fermions. Of course, to be fair, we have to know that this is not the only possibility. So having a standard model with only 2 generations, extending it by a 3rd generation is not the only way to account for CP violation. We'll see how this arises, why having 3 generations allows for CP violation while having 2 generations does not. But this relies upon the fact that we only have a single Higgs doublet, for example, in the standard model. So it's not a unique possibility. It's a possibility that apparently nature has taken, but we don't understand why this is so. So this goes back to one of the questions that I stated on earlier, one of the big questions of fundamental physics today, why we have 3 generations. So there are several related problems or puzzles within the standard model, which are related to flavor more or less directly. In particular, there is the observation of CP violation, as I already hinted above with this observation of the non-vanishing epsilon k. And within the standard model, it's very interesting. That there is a single CP violating parameter in flavor changing processes. It is not the only possible CP violating parameter in the standard model as a whole, but we already know that it's the only CP violating parameter which has a value which is significantly different from 0. So it's actually order 1. So the CP violating parameter of the standard model related to flavor is order 1, while the other CP violating parameters like the QCD theta term are highly suppressed. Which again, we don't understand why, but it's the way it is. And what is interesting with relation to this is we also know that even though the CP violating parameter related to flavor physics is order 1, on the other hand, we know that cosmological baryogenesis actually does require additional CP violating sources. So this one CP violating parameter, which is large in the standard model, is not enough to account for a successful baryogenesis. There's also a relation of flavor physics to the electroweak hierarchy problem. In that solving the electroweak hierarchy problem with additional degrees of freedom actually requires those additional degrees of freedom to lie close or below the TeV scale. Okay. On the other hand, as we will learn, especially on Thursday, if this new physics, if these new degrees of freedom lying at the TeV scale have a generic flavor structure, this leads to flavor changing neutral currents, which would be orders of magnitude above observed rates. And this actually leads to a so-called new physics flavor problem, which we will discuss on Thursday. I like to refer it as the new physics flavor puzzle because it's not a problem which we don't know a solution to. It's a puzzle where there are several possible solutions, but we don't know if any of those are correct. Conversely, we can also flip this argument around and actually argue that for any new physics with generic flavor structure, Flavour is able to probe such physics to very, very high scales. And again, we will demonstrate or illustrate this on Thursday. So up to scales above the order of 10 to the 5 TeV in some cases.
Nate, sorry, there is a question. Maybe it's better if you specify what you mean with the let-weak hierarchy problem, because Veronica didn't enter in the details.
Okay.
Yeah,
so let me just...
He's asking if this hierarchy problem is referring to the different quark masses.
Okay. Yes. No, it's not. It's not referring to the different quark masses. It's referring to the fact that the electroweak scale, or G Fermi, or inverse G Fermi, is much smaller than Planck scale. That's, I guess, a technical definition. So, saying differently, the scale of electroweak symmetry breaking, which is parameterized by the Fermi constant, is unstable under quantum corrections. And so the fact that there appears to be a higher physical scale in nature, which is the Planck scale, and there is a large hierarchy between those two scales, indicates there is a problem of describing or having a stable hierarchy, in a sense that if you perform perturbative calculations, then you will see that you need to fine-tune the parameters or the counter terms at each order of perturbation theory, or if you build a model which is able to predict the electroweak symmetry breaking scale in terms of some fundamental parameters, like this happens in grand models of grand unification, of gauge unification, then you see that you need to fine-tune the parameters of the scalar potential to give you a electroweak symmetry breaking vacuum, which is much small, with the electroweak symmetry breaking scale, which is much smaller, the Higgs wave being much smaller than the wave of the unified group breaking at the gut scale. I hope this answers the...
Yeah, definitely. Thank you.
Yeah, so, and just to add maybe on this, so just to understand, if you haven't discussed the electroweak hierarchy problem in detail, so why this requires some new physics at the TeV is typically what happens is that since electroweak symmetry breaking is not stable in quantum corrections, you need a mechanism to stabilize it. And typically, all known mechanisms to stabilize such a hierarchy invoke new degrees of freedom. And those new degrees of freedom need to be at the scale close to the electroweak symmetry breaking scale. And any hierarchy between these degrees of freedom and the electroweak symmetry breaking scale is not stable. So that's why, since electroweak symmetry breaking is at the TeV, it's a fraction of a TeV, but it's very close to the TeV. So then any viable, stable solution to the electroweak hierarchy problem should invoke comes with degrees of freedom at or below the TeV scale. So what we really mean is close to the electroweak symmetry breaking scale.
And Yanei, can you give an example of an operator that is constrained to such high new physics scale?
Oh, yeah, I will give the actually a list or a table of these operators with the associated scales on Thursday, but I can give you an example of a process which constrains possible new physics contributions to such high scales, and it's exactly the measurement of epsilon k. So the measurement of epsilon k, today we can predict the epsilon k within the standard model to around 10% precision. We can also measure epsilon k to around 10% precision. And if we then compute, if we phrase this in terms of possible additional contributions due to some unknown dynamics with some generic flavor structure, due to the particular flavor structure which enters of the standard model, which enters into the prediction or the value of epsilon k, which leads to a severe suppression of epsilon k. The value of epsilon k is very small. We'll see exactly how this plays out. But this suppression, which is present in the standard model, due to the particular structure of flavor parameters in the standard model, if it's not present by these new physics dynamics, and it has some generic flavor structure, it will typically lead to a severe constraint in such new physics, and will, in particular, in case of epsilon k, for some particular operator structures, which I will write out in details on Thursday, it can lead to suppression of these operators to effective scales up to 10 to the 5 TeV. These are like 4 quark delta S equal to scalar operators, if you want the technical jargon. But we will write them down explicitly, so you will know. You will have them out written out later. Right. So apart from all of these puzzles related to physics beyond the standard model, even within the standard model, there are a couple of puzzles which are present related to the flavor parameters themselves. So if we look at the standard model flavor parameters, and again, not even discussing neutrino masses, we observe that the standard model flavor parameters in the quark sector are both hierarchical. What I mean by that, for example, is that the masses are highly hierarchical between generations. For example, the up quark mass is much, much smaller than the charm quark mass, which is again much, much smaller than the top quark mass. In particular, the up quark mass is below, let's say, 10 MeV. The charm quark mass is slightly below or a GeV and a half, let's say, or slightly above a GeV. And then the top quark mass is 172 GeV or 173 GeV. And second property of standard model flavor parameters is that most of these parameters are small. Again, if we just reframe the restrict the discussion to the masses, we'll see that the same pattern plays out in the Ckm, so the mixing parameters as well. But if we just reframe this to the discussion of the masses, then we see that all the fermion masses, except the top quark mass, are much, much smaller than the electroweak scale, or in particular, much, much smaller than the masses of the W, the Z, and the Higgs, which would be a natural. So the weak scale is the natural scale for all masses in the standard model, except possibly the neutrino masses. But for all charged fermion masses, the weak scale would be a natural scale for all the masses. But we observe in nature that all fermion masses, except the top quark mass, which is at the weak scale, are much smaller than the weak scale. And this constitutes the so-called standard model flavor puzzle. And even though it's technically not a problem of the standard model, that's why I don't call it a problem, because standard model is perfectly able to parameterize the observed values of standard model flavor parameters and the masses and the mixing parameters. It is nonetheless a puzzle because the structure that we observe, this hierarchy in the parameters, points to some possibly unknown flavor dynamics, which could be at the origin of the standard model flavor parameters. Okay, so this sums up my rather long introduction to the concept of flavor, and let's continue now with the more in-depth discussion of flavor within the standard model. So we'll start very general. The fact that any local quantum field theory model, which we can describe with Lagrangian density, which you want to construct, can be uniquely specified by two requirements or two pieces of information, if you want. One is the symmetries and the pattern of symmetry breaking. And secondly, the representations of fermions and scalars in the model. And so let's consider these two requirements in the construction of the standard model Lagrangian. So first, what are the symmetries of the standard model? So the standard model has a large local or gauge symmetry, which is SU3 of color times SU2 left of weak isospin times U1 of hypercharge. And this gauge symmetry of the standard model is spontaneously broken by the Higgs mechanism to the unbroken standard model gauge symmetry, which, as we already stated, is SU3 of color times U1 of electromagnetism. Okay, and now the second piece are the gauge representations of fermions and scalars, and in particular in the standard model we have the following gauge representations. We have the left-handed quark doublets, so they are triplets under color, doublets under isospin, and with the hypercharge 1/6. Then we have the right-handed up singlets, which are again triplets under color, singlets under isospin, with the hypercharge 2/3. Then we have the right-handed down type isospin singlets, which are triplets, singlets with the hypercharge 1/3. On the left-hand side, we have the left-handed leptonic doublets, which are singlets under color, doublets under weak isospin, with the hypercharge -1/2. We have the corresponding right-handed singlets of color, singlets of weak isospin, with a hypercharge of -1. These are the fermionic representations. And then we also have a single scalar representation, the Higgs field, which is a singlet under color, a doublet under isospin with a hypercharge 1/2. And this is the scalar, which in the ground state of the theory has a non-vanishing expectation value. In particular, its neutral component under electromagnetism obtains a non-zero VEV, which is the electroweak condensate. Okay, so with these with these requirements, now we can construct the most general renormalizable Lagrangian adhering to these constraints, which will be the standard model Lagrangian. Okay, and we will split this Lagrangian in three terms. One will be the so-called kinetic standard piece, which is, or also called the gauge piece, which is very simple and symmetric, and is completely specified by the gauge symmetry of the standard model and the fermionic representations. It also contains three parameters of the standard model. And these are the three gauge couplings. The weak isospin gauge coupling, the hypercharge gauge coupling, and the SU3 of color, the strong gauge coupling. The second piece will be the Higgs Lagrangian, or basically it's the Higgs potential, and it parameterizes the electroweak symmetry breaking. And it contains two parameters of the standard model. It's basically the coupling of the Higgs square and the quartic coupling. So the mu term in the lambda term. And finally, this will be for us the most interesting part, is the standard model Yukawa Lagrangian. And this is the part which contains all the standard model flavor dynamics and all the standard model flavor parameters. Okay, so let's proceed by actually writing out the standard model Lagrangian, all the pieces out explicitly, and we'll start with the so-called interaction basis. And this is the basis where the gauge interactions are diagonal. And let's start with the kinetic or gauge piece. And it can be written out as a sum of terms where the indices I, J are flavor indices as before. So they go over all three generations of fermionic fields. And we also sum over all gauge representations. So here the fermionic field psi goes over all fermionic representations that I listed above. And the terms all have exactly the same form. They are just the gauge kinetic terms for fermions, can be written out in this way. And I've explicitly added this delta function in flavor space to explicitly state that in this basis, that the so-called interaction basis is defined by having these gauge kinetic terms flavor a universal. They are also CP conserving. Because they are Hermitian. Now let's also define the gauge covariant derivative which appears in this term, which is as usual normal derivative plus I strong gauge coupling times the gluon gauge field times the generator of SU3 of color, which I denote as LA, plus I, the weak isospin gauge coupling, times the W gauge boson field times the generator of SU2, and then finally plus I G prime, the hypercharge gauge field times the hypercharge of the particular, corresponding to the particular fermionic representation. So here, LA, as I said, oh, I think my tablet froze. Just a second, I'll try to reconnect it. Okay, so let's see if it works now. Okay, I apologize. It seems that something went wrong with my tablet. Ah, no, it's back on. Okay, so you see it again. Okay, so as I said, LA are the SU3 color generators. TA are the SU2 left generators, so these are matrices. And Y are the U1 hypercharges. Okay, so these are the gauge kinetic terms for the fermions, but then, of course, we also have the, so let me do it this way. We have the gauge terms themselves, for the, so the kinetic terms or the interaction terms for the gauge fields themselves. So in addition, we need to write out the terms for the color fields for the weak fields and for the hypercharge field. Okay, so we will not be concerned with these last three pieces, so I'll just write them out for completeness. So this is the gauge kinetic piece. Now let's write out the Higgs part. It's so the Higgs potential in particular will be comprised of two terms. So the square and the quartic term. And we can quickly see that it's also S is the gauge kinetic term of the fermionic fields, which is Flavour universal CP conserving. There are no Flavour parameters in this part, but it's also interesting that it's also CP conserving. Okay. Now, before writing out the Yukawa piece, the Yukawa term, let's briefly discuss the Flavour symmetry of these terms that I've written down, namely the Star model gauge kinetic and the Higgs terms, in fact, have a very large global Flavour symmetry. And it's related to independent unitary rotations in flavor space of the 5 fermionic fields. And so let's define this. So we have a global flavor symmetry of L kinetic and L Higgs. And we can write the so-called Stalmol flavor global symmetry group as, in absence of the Yukawa terms, to be fair, as a product of SU3 Q related to flavor rotations in the quark sector, Q, because we have 3 different gauge representations of quark fields, times SU3L squared. We have 2 leptonic gauge representations. And of course, to be complete, we have a U1 to the 5th factor group as well. Because in fact, we have U3 to the 5th, which is the total symmetry concern. Now, these semi-simple groups, flavor groups, are SU3Q cube is in fact a product of SU3Q. So SU3 rotations of the Q fields in flavor space times independent rotations of SU3 flavor space of U fields and SU3 flavor rotations of the D fields. And similarly, the SU3 leptonic squared is in fact SU3L times SU3E. And finally, this U1 to the 5th factor can be parametrized, so that it's not a unique way to parameterize this U1 to the 5th, but conventionally one parameterizes this U1 to the 5th in terms of U1 baryon number times U1 lepton number times U1 hypercharge, which is, of course, gauged, times U1 so-called Peche-Quinn, which is broken by the fact that the down-type quarks, right-handed down-type quarks and right-handed leptons, charged leptons, have different charges. And finally, one can choose another one additional U1 factor, and conventionally one often chooses this to be U1E, let's say. So you can check explicitly for exercise if you want how you can embed this U1 to the 5th into the whole U3 to the 5th flavor symmetry group of the fermionic part of the Stalmon model without Yukawa interactions. Okay, so this is the flavor symmetric part. Now let's finally introduce the flavor part, in particular the Yukawa term. So the Stalmon model Yukawa Lagrangian can be written as a sum of terms. In particular, we have the down-type Yukawas with flavor parameters, flavor indices ij, and is of the form QLI bar phi dr j plus the up type Yukawa term QLI bar phi tilde URJ plus the charge lepton Yukawa Li bar phi ERJ, since these terms as written out are not manifestly Hermitian, we also need to add the Hermitian conjugate terms to these. Now I've introduced a notation of phi tilde I, which is defined as epsilon ij being the two-index antisymmetric Levi-Civita tensor times phi j. Or one can also write it, of course, in matrix notation as phi tilde being I times sigma 2 times phi. So we see now that as written out, this Yukawa term of the standard model is in general now flavor dependent. This is because the Yukawa matrices are not necessarily proportional to the identity, and in general can also be CP violating because these terms are not manifestly Hermitian. Now let's see how these terms induce the breaking of our global large flavor symmetry of the gauge kinetic terms. So in particular, when the Yukawa, when we turn on the star model Yukawas, we can observe the following breaking pattern. So if we start from the bottom, so the U1E symmetry is broken by the fact that the lepton Yukawa is different from 0. Technically, in fact, is that the rank of the YE dagger is 3. This is actually the fact that finally breaks YE. On the other hand, so next we have U1 Peche Queen, which is broken by the fact that the product of YU times YD is not null, and also that the product of YU times YE is not null. This somewhat depends on the Peche-Queen charges that one assigns to the fermions, but in the most conventional case where one assigns one PQ charge for the up type right-handed fields and another one for the down type and electron and charge lepton right-handed charge lepton fields. This is the condition that that arises. And then we have the SU3Q times SU3U is broken completely by the fact that the up type Yukawa is not proportional to the identity. Now, in fact, again, technically, the up type Yukawa actually breaks SU3Q times SU3U down to a discrete Z3 symmetry, which is read with the center group of SU3. We also have SU3Q product with SU3D, which is similarly broken by the fact that the down type Yukawa is not proportional to the identity. Again, up to a Z3. And in fact, what is important in this breaking is that the up and the down Yukawa matrices do not commute. So they cannot be diagonalized in the same basis. And then, only then, you actually break all of these flavor symmetries.
Yeah, Nate, one question.
Mm-hmm.
How could we see it easily if the U1 Pechi queen is broken by the products of y up, y down, and y e, y e?
How you could most easily see? Okay, so one way is one possibility is to actually use the so-called Spurion analysis, which I will introduce next, and you can check that these Yukawas, actually these products, have non-trivial transformation properties under the U1 PQ, and since they are non-vanishing, then they break the corresponding symmetry. This is probably, although it's not the most intuitive way maybe to do it, but it's technically the most straightforward, at least for me. Otherwise, you can probably intuitively understand the fact that since y up and yd and y up and ye have different charges, and these Yukawas cannot be diagonalized simultaneously, then you see that this field. So yes. Yeah, so okay, one way to actually, if maybe a simpler way, which does not completely prove it, but it's maybe easier to understand, is that if you turn off either the up Yukawa or both the D and the E Yukawa, then you can still freely rotate those fields such that you can preserve the PQ charges. That's another way to see it. I don't know if this sufficiently answers the question.
It does.
It will be probably easier to see with the Spurion analysis than you can actually manifestly see this happening in practice. Okay, so let's complete this pattern of breaking of the standard model flavor symmetry. So next we have SU in the lepton sector, we have SU3L times SU3E, which is broken by the lepton Yukawa, charged lepton Yukawa, down to a product of 3 separate U1 factors, the corresponding to each charged lepton flavor. And so, in summary, if we now see the residual global flavor symmetries after switching on all the Yukawas, we obtain the standard model global symmetry group in presence of generic Yukawas. And this corresponds to, so we haven't touched upon the U1 baryon number, and we also have 3 separate U1 lepton numbers. Okay. Now it turns out that in presence of quantum anomalies, these are not proper symmetries of the quantum theory. So what is left, in fact, is only a single U1, which is U1 B minus L. But we will not delve into this part of physics. Now we can go back and actually phrase what we called flavor physics in terms of symmetries. With this discussion that we just had, in that interactions which break SU3 Q times SU3L squared, so interactions which break SU3 Q cubed times SU3 L squared are what we call Flavour violating. So we say they're Flavour violating because they violate these symmetries, these global symmetries. And as we've seen right now in the standard model, these are the Yukawa interactions. So there is a very powerful technique which one can use to actually analyze in detail this pattern of breaking of symmetries, which is called so-called Spurion analysis. So I see that I'm running a bit short on time. So let me maybe switch for this last part to the slides because it will be a bit faster. So everything that I've discussed even on the whiteboard is actually also present in the slides, which you will obtain. So even if something was not easily readable in my handwriting, you will still be able to go back and look it up in the slides. So let me just find this analysis. Yes. So let me share now. Keynote slides. Okay. So there is there's the following technique to count the standard model. So in general, to count the parameters that enter in a pattern of symmetry breaking. So, and it goes as follows. Let's consider we start with a global symmetry group, GF, like we had in the standard model with the global Flavour group, which has some n total generators, group generators. Now, if we have a pattern of breaking where this global group is broken to a smaller subgroup, which now has n total minus n broken generators, then one can show the number of physical parameters in this theory is given by exactly n general minus n broken. So we can do this parameter counting exercise within the standard model, where we have this U3Q. So if we just restrict our discussion to the quark sector, we have U3Q times U3U times U3D being broken down to U1 baryon number. So the number of total parameters is 3 times 9. In particular, we have 3 times 3 real parameters and 6 phases, which can be used to parameterize unitary 3x3 matrices. And the number of broken generators is the total number of generators minus 1 phase, because the U1 baryon number is completely parameterized by 1 phase. So we have the number of broken generators, so number of parameters is 9 plus 17. So 9 real parameters plus 17 phases. And the number of parameters which parameterize the Yukawas is actually, so we have 2 Yukawas, and each Yukawa, being a general 3x3 matrix, is parameterized by 18 parameters, namely 9 real and 9 imaginary numbers. And so using the above formula, we obtained that the number of physical parameters, which can be measured in experiments, is given by 9, is in total 10, and in fact, it's 9 real parameters and 1 phase. And we will later see that these parameters correspond to 6 quark masses, 3 Ckm angles, and 1 Ckm phase in the quark sector. So as an aside, they are also very much connected to our discussion of flavor, especially tomorrow, will be the notion of discrete standard symmetries. Again, if we start very general, we know that any local Lorentz invariant quantum field theory needs to conserve a product of charge conjugation, parity, and time reversal. And from this, we see that in any such theory, CP violation is uniquely related to time reversal violation. And in particular, if now we consider the standard model, we know that by the fact that the gauge representation of standard model fermionic fields have different chirality, we know that C and P individually are maximally violated in the standard model. And this violation of C and P is independent of the parameters of the standard model. It's just by construction, because we have chiral gauge representations, fermionic gauge representations. On the other hand, CP violation in the standard model depends on parameters. And as we've seen, the only parameters which are related to CP violation in the standard model flavor sector are the Yukawas. And the condition of CP conservation in the case of Yukawas would be that they are Hermitian. And in fact, I will not show this here, but I believe you will do an exercise of this, that you can actually construct a reparametrization invariant measure of the amount of CP violation or the presence of CP violation in the standard model, which is called the so-called Gyroscopic Variant, which is written out explicitly here. And again, you may wonder why this particular form. And this is related to the fact that since not all of the general parameters which parameterize the standard model Yukawa interactions are physical, as we just discussed, some of the phases, so if we go back, we see that the general parameterization of Yukawa matrix in the quark sector, in fact, has 18 phases. And there is only a single physical phase. And so this is reflected in the fact that we have a single invariant measure of CP violation, which is uniquely determined by this particular, so imaginary part of the determinant of YD dagger commutator with YU dagger. And so what is stated here is actually that the condition of CP conservation would be that this particular Gyroscopic invariant would vanish. And in the standard model, as we'll see, it does not vanish. So we have CP violation in the standard model. So as a historical aside, the experimental discovery of CP violation in kaon decays, namely the measurement of epsilon k, led to the Nobel Prize in 1980. While, let's see, so I'm running out of time a bit. Let me just see. Yeah, so Luca, I only need a couple of minutes. Can I just finish this?
Of course, no problem.
Okay, thanks. So all of the discussion that we had so far was actually done in a fairly basis-independent manner. So we were able to count the number of standard model flavor parameters and determine the presence or absence of CP violation without actually going to any particular basis. In fact, we didn't even specify the ground state of the theory explicitly and expanded around it. But if we want to actually discuss processes and measurements of these parameters, then we actually need to go and now frame our discussion around physical excitations of fields around the ground state of the theory. So we do that by now invoking the Higgs vacuum excitation value, and then we observed that in this case, the Yukawa interactions are related to the mass matrices of fermions. And now we can define the mass basis to correspond to a basis where these mass matrices are diagonal. And in general, we can move between different bases of fermionic fields in Flavour space using unitary rotations. So in general, we have separate rotations available with which we can rotate each gauge representation. So we can rotate the quark left-handed doublets with a unitary rotation in Flavour space. And so we can do it also with the up and the down type right singlets, isospin singlets. And doing this, this will transform the corresponding Yukawa matrices by just multiplying these unitary rotations from left and the right hand side. Now, if we want to rotate the Yukawa matrices to the diagonal, we in fact, in general, since the up and the down Yukawas do not commute, we need to perform separate rotations, so different rotations on the up and the down quark Yukawas, which means that, as we see in the bottom two lines here, there are two separate rotations of the left-handed quark doublets, which are needed to diagonalize the up and the down Yukawas. So one cannot do it with the same rotation in general. And so one can define now in the mass basis with the diagonal mass matrices, which are related to the diagonal Yukawa matrices via the prefactor involved in the Higgs value. So in the following, I will denote the small lambda U and small lambda D as the Yukawa matrices in the diagonal mass basis. Now, one can see that using this, because we have this freedom of SU3 Flavour rotations in the right-hand fields, which are completely independent, the parameters of these SU3 rotations are not physical. They can be reabsorbed into our definitions of the right-handed quark fields. However, this is no longer true for VQ, because there is not a single rotation which can diagonalize both the up and the down Yukawas. And so, since the up and the down mass matrices do not commute, then the VQU and VQD are not the same, and their product is not a unit matrix, but is a physical is a related. So parameters of this matrix are observables. We'll discuss in detail tomorrow which parameters or which combinations of parameters of this matrix are observable. And this is called the Ckm matrix by its authors, namely Kabiba, which defined a related matrix in a two-generation case, and then Kobayashi and Mascala for the three-generation case, which also led to the prediction or explanation of the observation of CP relation in Flavour processes, namely in chaos. And in particular, this construction led to Kobayashi and Scalars to obtain, to be awarded the Nobel Prize in 2008. Now, one can go back to the standard model Flavour Lagrangian now in the mass basis, and one can check, you can do it as an exercise to check that even in the mass basis, after performing these unitary rotations in quark Flavour space, the gauge kinetic terms related to neutral currents, so namely the interactions of quarks with gluons, photons, and weak Z bosons, remain Flavour universal and diagonal. On the other hand, the charge current weak interactions, so those interactions of quark fields to charge W bosons, become non-universal. So this Ckm matrix enters now so even though it originates from the Yukawa sector, in the mass basis, it actually reflected in the non-universality of charge current weak interactions, because they involve both up and down fields, which we had to rotate with different unitary matrices to bring the mass terms to the diagonal. And finally, the Flavour indices are also carried, of course, by the Yukawas, which is reflected in the couplings of the Higgs boson to the fermions. In particular, the Yukawa interactions of the Higgs boson in the mass basis remain diagonal, but they become, of course, non-universal because they become directly proportional to the fermion masses themselves. Okay, so since I'm fairly over time, let me stop here, and we'll continue the discussion of how to actually test and probe this Flavour structure of the standard model in detail tomorrow.
Okay, Yanei, but before you stop, 2 questions.
Sure.
Related to the Ckm variant, and the student asked why the Ckm variant parameterizes the CPA violation and how to see that.
So you're asking about the bottommost line here.
Yeah.
Yes. So let me see. So what you want, I'll try to describe it in general terms, not to go too much into technicalities of how I actually derive this. But in general, what you want is you want an invariant of the matrices. So what I mean by that is that it's basis independent measure. And so, of course, you need to look for matrix invariants like the traces and the determinants and so forth. And the relevant measure which vanishes only in presence of CP conservation turns out to be the determinant of the commutator. And this, you can partly understand it from the following. If the up and the down Yukawas were to commute, then there would be no Flavour violation at all, because the Ckm would be the unit matrix and would also be a CP conserving. Okay, so first we see that whatever measure of CP violation we have, it needs to reflect the fact that any Flavour actually vanishes if the up and the down Yukawas commute. Secondly, one can also do the exercise and show that if a quark was massless, then again there would be a U1 symmetry related to individual rotations of the left and the right-handed chiral components of that quark Flavour, and then you could also absorb a phase there. So you could also make again you could absorb one CP violating phase in that quark Flavour rotation, quark phase rotation, chiral rotation. And so it turns out that the relevant matrix invariant, which again vanishes if any quark mass is 0, is the determinant, because it's the product of the eigenvalues. And so if all the eigenvalues, if one of the, in this case is the difference of eigenvalues. So if one difference of eigenvalues would be vanishing, then you would of course again get 0. And finally, you want a phase, a CP violating phase. So it actually has to do with you have to probe the imaginary part of this determinant. And so this is now in very broad terms, the description, how you arrive at this formula.
Very good. And the last question, if you can demonstrate how the phase absorption works for the definition of the Ckm matrix, how to move from the 6 generic phases that could be there to one single.
Okay. to go back. So we see that in general, a 3x3 unitary matrix could have 6 phases, right? And we just said that the Ckm only has a single phase. Now, one way formally to do it is to use this formula, then you know it has to be one phase. But you can also do it more explicitly by noting that you have since you even in the final description, when you have 6 massive fermions, these are 6 Dirac fermions, you have the freedom to absorb relative phases of 5 of those. So using the independent phase rotations of these fermionic fields, you can absorb 5 out of these 6 phases, and then you're left with 1 phase which you can no longer observe. So it takes a bit of work to actually work it out, so you can actually explicitly do all the field redefinitions that are allowed by the gauge symmetries of your theory in the broken phase. And then you can see that you cannot absorb 5 of these phases, but you're left with 1 phase which you cannot absorb with any kind of rotation which would respect the symmetries, the gauge symmetries of the Salmon.
Okay, perfect. I don't see any other question. So I think that we can close the lecture here. So thanks a lot, Yerney, and see you tomorrow morning. If you have any material that you want us to put already in the Indico page of the school, just send to me and I will upload them.
Okay, thank you. Yes, I will send them to you soon.
Very good. And in this case, let's see tomorrow morning at 10.
Okay, see you tomorrow.